To find the perpendicular bisector, you need to bisect the segment. So that means find its midpoint and then pass a line perpendicular to the segment through that midpoint. So if you just choose each side, Control M will find its midpoint, then select that side, construct a perpendicular, and do the same thing for each of the others. Control M to find a midpoint, select the side, construct a perpendicular. Now, do we need this third one to find our point of concurrency? No, we already know where it's going to be, right? It's going to be in this intersection right here. What does the third one add to? Again, what it allows you to do is verify that that is, in fact, the correct point. And then you can select that point. And I'm also going to go back in. I'm going to turn these into a lighter color. I'll turn them into greens. Okay, so that you can see this point. Now, this point right here is called the circumcenter. Do you think this point will ever fall outside the circle?
Yes.
And drag a point and see. It is possible that that circumcenter will lie outside the triangle. What kind of triangles are formed when that circumcenter falls outside? What classification of triangle? Obtuse, right? And when it's on the inside, it's acute. What happens when the circumcenter is right on the triangle? What kind of a triangle does it look like? And it's a right triangle. So again, you can model that or view it on your own here. Okay, now it says that this is the center of a circle that can be circumscribed about the triangle. What that means is, if you want to create a circle that passes through all three of these points, easiest thing to do, just choose the compass tool, begin on that circumcenter, and drag the point until it intersects one of those vertices. That's going to lock it in. It'll lock it to that vertex. So no matter which point you move now, that circle will remain what's called circumscribed about the triangle. It'll pass through each of those vertices. And now the utility of this point is, let's say you had a cell phone tower and you wanted to reach 3 main cities, and you knew what the radius of the tower was. Is there a place that you could put that tower so that it would have an equally strong signal to each of those cities or locations? And that would be found by finding this circumcenter. And because all 3 of these vertices of the triangle are the same distance from this circumcenter. So you could place this would show you, if given 3 cities, where to place an antenna or signal of some sort to reach all 3 cities or locations with an equal strength. Okay, now what I'd like you to do is, on this same diagram, I want you to construct the in-center of the same triangle. Okay, so if you remember how to do that, the in-center was the point of concurrency of the 3 angle bisectors. Okay, so bisect each angle, and then find where those intersect. So you take the angle bisectors. Again, I made mine a different color. That's just so you can see. Is the in-center ever going to fall outside the circle or outside the triangle? No. What happens when you line the in-center and circumcenter up when they're the exact same point? What kind of a triangle does it look like you're creating? Looks like equilateral. We'll come back to that, but are there any other types of triangles where this appears to be the case? No? So we'll look at that in a little more detail, but when the in-center and circumcenter are the same points, the triangle that you're dealing with is equilateral. Bless you. And remember, when you're constructing the inscribed circle, you have to create a radius from the in-center that extends and meets the side of that triangle at a 90-degree angle. So if you construct a perpendicular from the in-center to one of the sides, it doesn't matter which side. Again, I'll change the color here, make it a lighter color. So this blue segment find where that intersection is. And now if I drag a circle from the in-center to that intersection, again it locks in as the inscribed circle, so no matter where I move this, that will always stay inscribed within that triangle. Can that inscribed circle and the circumscribed circle ever be the same? No. And it should make sense. It's impossible, right? Because if it was the same, it couldn't be inside and outside the triangle all at once. Okay. But again, when you're looking at this equilateral triangle, and you can see the relationship of the inscribed and circumscribed circles become concentric circles. They share the same center point. All right, are there questions about this point of concurrency? And there's no additional properties other than what we looked at here. And the main relationship in this is that point is equidistant from all three vertices of the triangle.